Hey everyone, we are starting our new unit. This is Unit 7, which means we are looking at inference for quantitative data, which means we are putting aside proportions and we are looking at things that we are going to be able to take the averages of. So we're starting to look at population means and sample means and things like that. So that means we're putting aside a bunch of the p's for now. We're looking at mu's and x bars. And we want to start by looking back at Chapter 8, which was all about confidence intervals. And we know the idea behind confidence interval is to estimate something about the population. So now we're going to be estimating population mean. And we want to know for our essential question is, what the fudge is a t-distribution? Or how is a confidence interval for means different from a confidence interval for proportions? Okay? Well, the first thing that we need to understand is, well, how did we construct a confidence interval in the first place? Let's kind of remind ourselves a little bit. We always start with a best guess, and we call that best guess our point estimate, right? And then we need to give ourselves some wiggle room, because we know we could be a little bit off. And that wiggle room brings us to a lower bound for a confidence interval and an upper bound, and that tells us our plausible range of values for whatever it is that we're trying to estimate, right? And we think, well, how do we get to that lower bound? Well, remember, that's just all based on the margin of error. So we take away the margin of error from the point estimate to give us the lower bound, and then we add the margin of error to the point estimate to give us the upper bound. So that gave us a very general idea of how to find a confidence interval, no matter what it is we're trying to estimate, is we take our best guess for it, the point estimate, and we add or subtract from it the margin of error, okay? So let's think back to some of the stuff we did back in the beginning of Chapter 8 and Unit 6 when we were estimating P, right? Remember that this is the population proportion, right? So this is the thing we don't know, but we're trying to estimate, and we said the best way we can do that is to take P hat, that's going to be our point estimate, that's our sample proportion, and we add or subtract from that a critical value multiplied by the standard deviation of the sampling distribution, right? So the standard deviation of the sampling distribution, though, we remember that we couldn't actually work with that. That wasn't allowed because that formula was found by taking the square root of P times 1 minus P over N. We can't do that because we can't use P. We don't know what the population proportion was. So instead, we said it was going to be P hat plus or minus Z star times the standard error of P hat. And the standard error of P hat, it was pretty simple, right? It's just going to be changing our margin of error formula to this critical value Z star times the square root of, instead of P times 1 minus P, it's P hat times 1 minus P hat, and that's all over N. Right? So those are the different components that make up the confidence interval for proportions. But again, we're trying to shift away from that. But we want to see what the parallels are between proportions and means. Well, if we used P hat to estimate P, then it only stands to reason that we should use a sample mean to estimate the population mean mu. Well, what symbol do we use for the sample mean? That's x bar. So if we use x bar as our point estimate, then we can think about, all right, that's going to be then, I got this figured out, it's a critical value, Z star, times the standard deviation of the sampling distribution of the sample mean, sigma sub x bar. And so we think, all right, that's easy enough. Z star times sigma sub x was very simply sigma over square root n. We think, all right, not that big a deal. Now this works great if we know sigma. The problem is we generally don't know sigma, and this should make sense because remember that sigma is the population standard deviation. We don't know what the population standard deviation is. If we knew what that was, we would know what the population mean is. The whole idea is to take something from a sample and a sample only to try and estimate what the population is and how it's behaving. So the problem here is we don't know what this guy is. When we don't know what that is, then we have to use something else. So what is that something else? Well, let's think about what happens if we use the standard deviation from just a single sample to try and estimate the entire variation for the entire population, okay? Well, we're going to end up looking at a diagram like this, okay? The one on the bottom here, this is your sampling distribution of x bar, right? And remember that the whole idea behind why we are able to create these sampling or why we're able to create these confidence intervals, because we know how each individual sample should behave when we compare it to all possible samples, or we compare it to the sampling distribution. So here, this shows us that we have the approximately normal sampling distribution of X bar, and we have a sample mean compared to a population mean, and then we have this guy here, sigma, okay? And this guy here, sigma, is going to be used to find a critical value, a z. But again, we don't know what that is. So what are we supposed to use? Well, instead of using sigma sub x for this whole thing here, we don't know what sigma sub x bar is, so instead we have to use the standard error. The same reason that we had to use standard error when we were talking about proportions, we have to use standard error here. And we have to use some kind of estimate for that. So we are going to use the standard error of x bar. And get your giggles out of the way now, because yes, this is indeed the notation for the standard error of x bar. I didn't come up with it, but hey, that's what it is. So it's SE sub x bar, and the formula for SE sub x bar is when we don't know what the population standard deviation is, so we have to use a sample standard deviation, S sub x, in place of the population standard deviation, okay? So we're actually not going to use this formula for margin of error, okay? We're going to use something else, and we'll kind of build it as we go. But what we want to focus on right now is that what do we notice about when the distribution, the sampling distribution, if we change to this guy right here, the SE sub x bar. Would you say that this looks like it's approximately normal? Yeah, it's pretty close, but what else do you notice about it? It's a lot more variable. Look at how much more spread it has. So in fact, because it's so much more variable, this is not quite normal. Since it's not quite normal, we can't use the z table and we can't use the normal distribution to make an approximation for how the sampling distribution would behave. We have to use something else, and this something else is called the t-distribution, okay? So, long story short, the distribution data is not normal anymore. It's a little more spread out, and we call this kind of distribution a t-distribution. So the t-distribution is going to be the basis for all of our confidence intervals for looking at population means, okay? And then instead of having z star for a critical value, we're going to have this thing called t star. And the t star is going to be our critical value. So let's take a look at this thing called t star, the critical value, and how to find it. Well, just the same way that we had a z table, we actually have a t table. And we can use a t table to find t star, just like we use that z table to find z star. So if t star is now our critical value, then we can calculate the confidence interval for mu. Now, how do we use a t-table and what does it look like? Well, it's going to have columns and rows just like what we saw with the z-table, except we not only have a top row, but we also have a bottom row that we're going to want to pay attention to. And we're going to introduce this new thing that is mostly beyond the scope of this course. It's called the DF, which stands for degrees of freedom. Now, we're going to use it a lot, but I'm just not going to really strictly define it or try and interpret it, because it's very complicated, and I find it slows most students down. But the degrees of freedom is really simple and easy to find, and it is n minus 1. So remember, little n, that's your sample size. So to find your degrees of freedom, which is what we're always going to need whenever we're working with t star or we're trying to make some kind of inference about means, we need the degrees of freedom. Okay? Degrees of freedom essentially is saying, like, look, I understand that I'm making an inference and I need a certain amount of error to make my estimates a little bit more conservative, and kind of letting you know that. That's statistically a very, very, very basic way of describing what it is we're looking at. Okay? So I don't want you to freak out too much about this. It's really simple. We just use degrees of freedom n minus 1. Now, we are going to then have to need the confidence level, just the same way that we needed a confidence level to calculate z star. And the confidence level is going to be found in either the bottom row or the top row. And I think you're going to want to focus on using the bottom row for most of the t-tables that we find. It's going to be a lot easier. Okay? And then we want to find the intersection between the degrees of freedom and the confidence level. Okay? Those are the two things that we're going to want to pay attention to. All right? So let's go ahead and transition over to the t-table, which you can find as table B in the back of your textbook, or you can use the attached document that I've provided for you. And let's take a look at a couple of examples to try and find t-star. All right, so here is our t-table. As you see in the left-hand column, we have all this here, the degrees of freedom, okay? And then we are going to have down at the bottom the confidence level. I think this is going to be the easiest way for you to be able to see what it is that we want. And then we have also the upper tail probability. So this is kind of like the old school way that you would have worked with Z-star, but we're not going to worry too much about that. I'll show you once, but I'm not going to show you too much more other than that, okay? The difference here is that, you know, Z-star used to be on the left-hand column in the top row, but that's not how it's going to work with T-star. The T-star is going to be all of these numbers that are provided for you inside the table. That's where we're going to be looking. Okay, so in a lot of ways, I actually think this is easier to work with. Now, let's go ahead and turn to our examples. And let's see, for the first three examples, we're just going to be finding T-star. This is a really important skill. So the first thing we've got is we want to find T-star for a 90% confidence level based on a random sample of 10 observations, okay? So I want to write out the couple of things that I need. My confidence level is 90%, and then I have a sample size of 10, okay? And then I want to calculate my degrees of freedom, which is easy enough. We take our degrees of freedom. It's n minus 1, so that's 10 minus 1, and that's 9. You don't need to write out all that stuff. You can just show me. df equals 10 minus 1, 9. Boom, done, okay? Now, what we could do is try and think about how did we find Z-star when we were using confidence intervals before. And remember what we did was we drew out our normal curve. Remember, this is approximately normal. It's not quite normal. It's got a little bit more variation. We put in our confidence level in the middle. And then we said if 90% of all samples will make up that middle 90%, then that means we've got 5% of all samples on the outside, right? And so that's where we'd want to look for. And we said we look inside the table for that, but not with T-star, okay? What we look for here is we look for our degrees of freedom, and we look for this guy. Now, this is the tail probability. So the tail probability is going to be in the top row, that's 0.05, and then we look for the degrees of freedom, that's 9, and we find the intersection between the DF and the tail probability, and that's 1.833. So my T-star is equal to 1.833. And there it is. Boom, done. Super easy, right? But we think, wait, you said I was supposed to use my confidence level. I didn't use my confidence level. Well, this is why I really like the confidence level, because you actually don't even need to draw out the normal curve. You don't need to find the tail probability, because almost every one of these t-tables has, look down at the bottom row, the confidence level, 90%. And look at what column that corresponds with, the same one that has that same tail probability. So we'll be able to find it that way. So instead, work with the bottom row, and then find the intersection between the bottom row, that column that's pointing to, and the degrees of freedom row. Okay, let's go ahead and take a look at the next example. And we want to find now a T-star for a 90% confidence level based on a simple random sample of size 95. So n equals 75, and that means my degrees of freedom is going to be 74. Oops, 74, there we go. So we go back to our table. Let me say, all right, let me clean up a little bit here. And we have the same confidence level, 90%, so that's good. And we think, well, wait, where's 75 for my degrees of freedom? Or 74, I don't see it. So which one do I choose? Do I choose 60 or do I choose 80? And most of you think, well, I'll choose 80. It's closer to that, right? And the answer is no. We want to be more conservative. So what we actually do is say what's going to make the more conservative estimate is actually going by the lower sample size. So we want to choose this for our degrees of freedom. So I'm going to make a quick note back here and say that my degrees of freedom, since that's actually not, 74 is not on my t-table, I'm going to show that I'm using a degrees of freedom of 60, and then we can find the corresponding T-star that goes with that, and that's 1.671. Okay? So we have T-star of 1.671, and that's it. Last one, T-star of a 99% confidence interval with a random sample of 25. So I have a new confidence level. That means I need to look at a new column based on the bottom row. And then I have a degrees of freedom of 25 minus 1. So I'm looking in row 24. We'll go through here, clean up a little bit. Let me see, do we have 24? Yes, we do. And then do I have 99%? Yes, I do. So we look and see, all right, where do these two intersect? And they intersect right there at 2.797. That's my T-star. So this is really common for a lot of multiple choice questions, is you're going to have to do some kind of finding of t star, that critical value. You need to be aware of how to do this. Also, when we're making our intervals, the t star doesn't come up using our calculator to make the confidence interval for some reason. I'm not sure why they didn't include it in the program, but it's not there. We want to provide it though, so it's good to make sure you understand this process. All right, let's go ahead and take a look back at our notes and figure out when are we allowed to use the t distribution and how do we actually make our confidence interval at this point. So when are we allowed to use this t distribution? Well, this is all based off of the normal approximation, right? It's an approximately normal shape, but it's a little bit more spread out, so it's not quite normal, which means which condition do we have to check in order to state that sample means are going to be approximately normal? And you might think LCC. Remember, LCC is for proportions, so not the LCC, no. When we were talking about means back in chapter 7 in unit 5, we had to look at the CLT, and we had two different ways that we could actually look at it. First of all, we know that we would have that approximately normal shape if our population is known to be normal, or if the CLT is satisfied, and that's that our sample is at least 30, okay? But here's the thing, since we're using something that's even a little less normal, we have a little bit more wiggle room. Even if we have a small sample size, as long as the sample has no strong skew or outliers, then we are okay to use the t distribution. We are okay to have t star as our critical value. So what does that mean? Now we should be able to infer pretty reasonably what conditions we should be checking in order to construct a confidence interval for a population mean. First thing, one of the things we always know, we have to have randomness, right? So we want to have a random sample, or if we are dealing with an experiment, then we need to have random assignment. Sorry about that. And then we have to also check our 10% condition, where we have to say that our sample is going to be less than or equal to 10% of our population. And if this is true, then what does that tell us? Again, this tells us that we are able to calculate the variability using the standard error of x bar. And we can use this formula, s sub x over square root of n. Okay, and then we have the last thing is that normal condition. So we have three different outs here that we can really look at. Do we have a normal population? If so, then we're okay. We can stop right there. Or is the CLT satisfied? If the CLT is satisfied, great, we can stop right there. And if finally neither of those two things are satisfied, if we have a sample that is less than 30, but there is no strong skew or outliers present, then that means we can go ahead and use the t distribution and we can calculate our confidence intervals. What does this mean? This is from our sample data, which means you will have to graph it if you are not shown this information. Okay, so let's take a look at some examples to put this together and see when can we actually use this t distribution and the confidence interval formula that we're going to construct. All right, so back to our examples. We're looking at number 4. For number 4, A and B, we want to just determine whether we can safely use t star as a critical value. So we have to check that normal condition, right? So let's go ahead and take a look at part A. We want to estimate the average time. Well, first of all, I have to know that t star is really only for quantitative information. So provided that this is quantitative, not looking at proportions or something that's categorical or qualitative, then we should be able to use t star. So we're looking at average time, it's quantitative, and we want to receive a coffee at a coffee shop. How long is it going to take? We take a sample of 5, and we have a dot plot of the sample data here. So the first part that we have to check is, do we see anywhere here that says the population of wait times is approximately normal? And we say, no, the population is not normal? No. It is not stated that it's known to be normal. It could be, but we don't know that it is. So, next thing is the CLT is satisfied. And we say no, 5 is less than 30. So that is out. So the last thing is we have to see, do we have any strong skew or outliers? And it looks like, man, that guy right there, this person that had to wait almost 6 minutes compared to everybody else that was less than 3 minutes, it looks like there's an outlier. And if there appears to have an outlier in the sample data set and neither of these other two conditions are met, we can say t-distribution is not okay to use. Okay, now let's go and look at B. We want to estimate the average height. Again, I'm looking at something that's average, so it's quantitative, so that checks out, good. Of high school students, the box plot shows the distribution of heights in centimeters for 100 randomly selected students. And I can actually, you know what? As long as it was a random sample of 100, I'm done. I don't know what the population is. That's fine. And we say my CLT says that 100 is greater than 30. So t-distribution is okay. And you think, wait, we've got these outliers here. I thought outliers are bad. Well, as long as the other two conditions are not satisfied, that's when we have to only be paying attention to outliers. If we have a large sample, we happen to have a couple outliers, that's totally fine, okay? Even though there are two outliers, since CLT is satisfied, t-distribution is okay. All right, let's go back and take a look, and now we can actually construct and interpret these confidence intervals. All right, we're near the end here. Now that we understand the t-distribution and the conditions that we need to check in order for the confidence interval to be valid, we can actually write out our confidence interval formula for a population mean. We start off with our point estimate, that's x bar. We use the critical value, not z star, but t star, and then we have our standard error, which we know as s sub x over the square root of n. And this is a little bit easier formula for us to remember, I think, than the one for proportions, but here's the thing, we don't even have to really memorize this thing. It's on your formula sheet, you can build it that way, or you can just use the calculator. So, what you want to pay attention to is doing a t-interval once you get into the confidence interval step, and then it's going to ask you for data input, and you have the option for data. That's if you had all of your individual data points into a list and spreadsheet, which we won't deal with that until a little bit later, just because it adds a couple more steps that I don't want to worry about right now. So you're going to choose stats for now, at least, okay? And we'll kind of move on from there. And then we'll be able to choose a sample size for a mean in a little bit. But for now, let's actually go and create these confidence intervals and interpret them. All right, so here is our example number 5. For their second semester project in AP Stats, these girls, Anne and Tori, wanted to estimate the average weight of an Oreo cookie to determine if the average weight was actually less than advertised. So they think there's shenanigans going on at the Oreo factories. They're actually making smaller Oreos than what they really actually are deserving to get. So they took a random sample of 36 cookies and found the weight in each one in grams. So we have an X bar and we have a standard deviation. And then we want to construct and interpret a 95% confidence level for the mean weight of an Oreo cookie. All right, so let's go ahead and start by writing out all the things that we know. We have an N that is 36, and our population size, we don't know how many there are, but we know that this is going to be all Oreos, right? So that's going to be a very large number, okay? And we had a sample mean equal to that was equal to 11.3921, and then our standard deviation from the sample was equal to 0.0817, and then we have a confidence level equal to 95%, and then we have a degrees of freedom of 36 minus 1, and that is 35. Okay, so what we can then start to think about is what's our t-star going to be. Okay, let's go ahead and take a look at t-star. That's where we want to look at the confidence level and the degrees of freedom, and just jot that down real quick. So I have this 95% confidence level, and a T star, or the DF was 35, but we have to use the one that is going to be a little less, or a little more conservative. And so then we look to see here what's the intersection between those two, and we get 2.042. That's going to be our T star. And I'm going to use the approximate symbols here, okay? Because we had to use 30. So my degrees of or my T-star is actually going to be a little bit more severe than this 2.042, but I'm using that as at least an approximation, okay? The next thing we should do is we should check all of our conditions and make sure that this thing is actually even going to be valid. So conditions, these are actually going to go a lot faster, guys, especially from what you're used to recently. We say that we had a random sample of cookies, right? We had a random sample of Oreos. We had our 10% condition. We know that's going to be satisfied because I'm hoping that they make a lot more than 360 Oreos. So we know that's going to be satisfied. And then we have to check our CLT, or population being normal. Well, our CLT is satisfied. 36 is indeed greater than 30. So that's satisfied. Look at that. Condition's done without a problem. Now, what do we do to actually make this confidence interval? I could do this by hand, but I don't want to. I want to use my calculator for it, okay? So let's go to a calculator. Let's open up a calculator page, and we're going to open up our menu. And we're going to choose option number 6, statistics. And then we will choose option number 6, confidence intervals. And we want to be really careful about this. Remember, what we want to choose is the T interval, okay? We choose T interval, and for our data input method, we don't choose data, we choose stats. And then we are going to have to enter in what is our X bar. Our X bar in this case was 11.3921. Tab down to our standard deviation, which was 0.0817. And then we had our sample size of 36. Confidence level was indeed 95%, so we're good to go. Go ahead and hit enter, and we have our confidence interval. It's going to populate for us. We have a lower bound 11.3645 and an upper bound of 11.4197. The X bar is like our point estimate. ME is our margin of error. Gives us the DF, but for whatever reason, again, it doesn't give me my T star. So let's go ahead and write out this stuff, and then we can interpret it. So again, the operation that we chose in our calculator was doing a T interval, and this was giving us 11.3645 as the lower bound and 11.4197 as the upper bound. It gave us a point estimate of 11.3921 and a margin of error equal to 0.0276. Everything else we've already got, so now we can just go ahead and interpret it. And this is that I am 95% confident statement. It's been a little while since we've done this, but let's remember, I am 95% confident that the interval from blank to blank, and my blanks here are 11.3645 and 11.4197 grams, captures what? Well, what is it that I am trying to make an estimate for? The mean weight of an Oreo cookie. Captures the mean weight of an Oreo cookie. Okay, so that's it. That's making the confidence interval and interpreting it. Easy peasy. Now let's go ahead and take a look at part B. So in part B, the question was, hey, are they actually getting shortchanged here? Well, we don't necessarily know off the top of our heads what's the advertising claim, so what they had to do is look at the back packaging and say that the serving size of 3 cookies was 34 grams. Okay, so what's 34 divided by 3? If 3 cookies is supposed to be 34 grams, then what is 1 cookie going to be? 34 divided by 3 gives us 11.333, and we want to know, is that plausible? Is that valid? Is that inside our confidence interval? And we say, no, It's not. 11.33 is not within our confidence interval, but it's on the low side. So what does that actually tell us? We're actually getting more than what we purchased. It might be a tiny, tiny bit more, right? We're talking about fractions of grams, which is an extremely small amount, but still. We don't have any evidence to suggest at all that they are shortchanging us, that they're giving us less Oreo for our money. In fact, they're giving us more Oreo for our money. So do we have any convincing evidence that they are false advertising? We say no. No evidence of false advertising. Since the interval is entirely above the claimed weight of an Oreo. All right, there you go. And for our next example, we have 2 more students doing a second semester project. They are taking 18 rolls of toilet paper, and they want to know, hey, how absorbent are they? So this is actually kind of an ingenious experiment they do. They poured 1/4 cup of water onto a hard surface and then counted how many squares of toilet paper it would take to completely absorb the water from these 18 rolls. Okay, now it's pretty handy because they give us all of the data that we need and gives us a lot of information, but really think about what is it everything that we need. We need a sample mean and we need a sample standard deviation and a sample size. That's it. That's all we need to know. Everything else is gravy. Okay, so all of this stuff is extra information that we don't need. It shows us that a graph of the distribution shows no skew or outliers, so that's good, right? Because we know we have a small sample size, we know that CLT isn't satisfied. We have no idea what the population looks like, but this tells us that one of our conditions is going to be checked. We want to construct a 99% confidence interval for mu, the true mean number of squares of generic toilet paper needed to absorb a quarter cup of water with 99% confidence. So let's go ahead and make that confidence interval, write down all of our given information. Okay, so we've got all of our given information except for our population, but we know that's all rolls of this brand of TP. And then we want to check our conditions for inference. Checking our conditions for inference, remember we've got 3 of them. Random selection or random sample. And then do we have no strong skew or outliers in our sample? And did we have 10% conditions satisfied? All right, so those are our conditions. Now let's go to our calculator and punch in the t interval to do this calculation. And here we have it. We have a lower bound of 22.98 and an upper bound of 26.89. Margin of error 1.95. I'm going to go ahead and round each of those. 22.99 is going to be my lower bound from my t interval. That was 22.99. Upper bound 26.90 if I'm rounding. And then we had a point estimate of the x bar, 24.94. We had a margin of error of 1.95, and that's enough. And we can write out our statement. I am 99% confident. All right, I'm 95% confident that the interval from 22.99 to 26.90 squares captures the true mean number of TP squares to absorb a quarter cup water. That's it. Okay, guys, hopefully that helps you out. Now let's go ahead and take a look at the last little step. I know this is a really dense lesson, but we got one last thing to look at, and that's choosing a sample size. All right, so if we want to choose a sample size for a population mean confidence interval, it's actually pretty simple. We just look at what is the formula that we would have to use for margin of error, and that is the t star times the standard error of x bar, so s sub x over square root n. Now, this guy right here, just want to be aware, sometimes notation is not great, and it is sometimes just given as standard deviation or sometimes even given as sigma, but we understand how it works. Okay, now what we need to do is we need to find an estimate for this s sub x or sigma. In the real world, we have no idea what this is, so what you do is you use some kind of pilot study or you use some historical data. Usually this is going to be given to you in the course of our class. Okay, so this is going to be given to you, and then we say we're going to find the critical value of z star. And I think, wait, I thought I was supposed to use t star. Well, we don't use t star because think about why not. Why to use z star instead of t star? Because t star requires that we know the degrees of freedom. We don't know what the degrees of freedom is because we don't know what n is yet. That's the whole point. So we must use z star. So that means you're going to have to draw that normal curve, and you're going to have to try and use the z table. But I'll show you a shortcut. Okay. Now we can also then just use that, plug in the things that we're going to replace with, and into this formula, and we're going to use this relationship that the margin of error is going to be greater than or equal to z star times s sub x over square root n, and then you're going to solve for that sample size. All right, so let's go ahead and take a look real quick at this example. It's going to go real fast, okay? Okay, so here's our last one. A counselor wants to estimate the average number of text messages sent by students at his school during school hours. He wants to estimate mu at the 99% confidence level, so there's my CL, with a margin of error of at most 2 texts. So my confidence level is 99%. Okay, and then my margin of error is going to be equal to 2. So I know that I have this relationship that I'm supposed to use. ME is going to be greater than or equal to z star times the standard deviation over square root of n. You see, oh, perfect. There's my standard deviation, about 9. So I'm going to use sigma equals 9. We can start plugging some things in. We know that 2 is going to be greater than or equal to z star times 9 over the square root of n, but I don't know what z star is. So let's go back to our t-table, because this is all you really need. Here's a nifty little trick. At the bottom, you'll see z star. Sometimes you'll see this written out as infinity. If you see it written out as infinity, you just have to realize that, hey, as the sample gets larger and larger and larger, the t-distribution actually approaches normality. Okay, and it actually approaches something that's approximately normal, so that way we actually can use the z-table. So all we have to do, really, is not look at any of this business here. We want to look at the 99% in the bottom row. And then we look at the infinity row at the bottom, and we see 2.576, and that's going to be our z star. Easy peasy. So we have 2 is going to be greater than or equal to 2.576 times 9 over the square root of n. Now we just have to do some clever manipulation with algebra. I'm going to multiply both sides by square root n. That's going to cancel out there. Multiply that by square root n. But then I also want to divide by 2. I'm just going to do this all in one step. If I divide this by 2, and then I divide this all by 2. 2's here cancel out. And look at what I'm left with. Square root of n is going to be greater than or equal to 2.576 times what was in my numerator, 9, and then 2 was in the denominator. And now all we have to do is get rid of that square. Well, how do we get rid of a square? Or how do we get rid of a square root? We square it, square both sides, square the entire thing here, square root gone, and I'm left with n must be greater than or equal to 2.576 times 9 over 2, and that whole quantity is squared. Okay? Punch that into your calculator, and we should end up with a sample size that must be greater than 134.374, and we know that we should be rounding up in this case. The n must be greater than or equal to 135. That's how many individuals we must be sampling. All right, you guys, that is it for today. Thanks for buckling in for a long one. Go ahead and get started on your assignment. Have a wonderful rest of your day.